Hello, I'm Allison Paredes, and my research is a review of the environmental footprint of the textile dye industry, mentored by Dr. Bremjot Kaur. As an introduction, textile relates to fabric and weaving, so the textile industry is an industry that composes clothing out of cloth or other materials. Clothing is fundamental to everyday living and is highly demanded in our growing population. In recent years, the textile industry has been boosted globally due to fast fashion, driving the growth of this industry globally. However, reports from the United Nations Environment Program and independent organizations suggest that people are buying more clothing just to throw them away soon after. The excess clothing ends up in landfills as waste. The first problem with textile dye manufacturing is the various chemicals and elements utilized. During the process, the textile industry uses around 8,000 synthetic chemicals, with 72 being toxic. Commonly used synthetic chemicals include flame retardants, PFAs, lead, chromium, phthalates, chlorine bleach, volatile organic compounds, and azo dyes, which compromise 60 to 70% of fabric colorants. For clothes to acquire their vibrant colors, dyes are used during textile processing to color them. About 10,000 various dyes are utilized through textile processing, mostly synthetic organic. Two main classification systems of synthetic organic dyes are based on chromogens, such as acridine, anthraquinone, azine, diphenylmethane, indigoid, methane, nitroso, oxazine, phylloxyanine, thiazine, tryph- tryphenylmethane, and xanin dyes. The second is based on application purposes, such as acid, basic, direct, disperse, fiber, reactive, vat, and mordant. Synthetic organic dyes most prevalent in the textile industry are azo, anthraquinone, and thylacyanine dyes. The second problem is that textile manufacturing requires vast amounts of water, which mixes with the chemicals used to create toxic effluent. The process uses natural or synthetic sizing agents pol- such as PVA to strengthen yarn. The modified yarn then undergoes the process of desizing, releasing glucose, resins, waxes, PVA, volatile organic compounds, starch, fats, etc., into the wastewater stream. The desized fibers or yarn then undergo scoring, which is a chemical washing process releasing detergents, sodium hydroxide, fats, solvents, wax, surfactants, alkyl benzyne sulfonates, al- alkyne phenol, and ethyl phthalates to textile discharge. The dyed fibers are then bleached using chemicals like sodium hypochlorite, para- peracetic acid, chlorine, hypochlorite, and hydrogen peroxide. This is followed by mercur- mercurization, which uses alkaline solid solutions to enhance the appearance of yarn material, releasing caustic soda, ZnCl squared, and cyclohexanols in the process and increasing the water's pH. The dyeing technique subsequently follows, requiring temperature and time to add color to materials and treating it with dye. The dyeing procedure releases reducing agents such as sulfites, dye stuff, mordant, lactic acid, metal salt, and cationic materials, surfactants, and chromophores in wastewater. Finishing is the final stage in the dyeing process, releasing salts, starch, and special finishes into effluent. Every step of textile manufacture, from the initial washing of the raw material to the final woven fabrics, utilizes a large scale of water. For an average sized textile mill, manufacturing about 8,000 kilograms of fabric daily, about 1.6 million liters of water are used. Consequently, the textile industry is responsible for about 20% of global industrial water pollution. After textile processing, the substance left is textile effluent, contaminated with potentially carcinogenic chemicals, dyes, salts, and heavy metals. Due to weak environmental regulations in developing nations, the textile industry releases 50% of the annual colored effluent into nearby bodies of water, polluting drinking water sources and harming aquatic ecosystems. Now we will be moving on to impacts of the two main problems of the textile industry, the first being geographic regions. As some of the biggest hubs of textile manufacturing, Asian countries like Bangladesh, India, and China are severely affected by water pollution from textile manufacturing. Many rivers, canals, and lakes in these countries have become severely to, polluted, some to death. Farmers have no choice but to use polluted water sources in some regions for irrigation. On the image on the top right, that is a river in China, and below that is a river or body of water in Bangladesh. For like an example, the second impact is on aquatic life and agriculture. When textile effluent is released as sources of fresh water, the high pH value solubilize in streams, increasing the internal temperature. High temperatures then decrease the solubility of gases in water, decreasing dissolved oxygen levels and increasing the biochemical oxygen demand or chemical oxygen demand. High levels of biochemical oxygen demand and chemical oxygen demand indicate excessive organic matter consuming oxygen and reduce the dissolved oxygen levels in the water. This causes stress, suffocation, and death in aquatic organisms and protects and promotes the growth of anaerobic bacteria that produce toxic substances. Also, as textile effluent enters bodies of water, the total suspended solids rise, increasing salinity and turbidity of the water, causing osmotic imbalances and preventing sunlight penetration, sustainable for photosynthesis and homeostasis. As stated before, wastewater irrigation is sometimes the only available method for agriculture in various world regions. The heavy metals in textile effluent can change the soil pH, cation exchange capacity, organic matter content, water holding capacity, soil fertility, and nutrient availability. Contaminated soil limits plant growth, biomass, chlorophyll biosynthesis, and carotenoid, causing plants to die prematurely and potentially dangerous for human or any type of consumption. The third impact is on human health. Inhalation and ingestion are common ways toxic chemicals and effluent can enter the human body. Nearly 40% of dyes in the textile industry contain organically bound chlorine, a known carcinogen. Also, dyes are among the most common organic dyes in the textile industry. These can transform aromatic amines upon ingestion via the action of the intestinal flora present in human or animal bodies, or under anaerobic conditions, having the potential for skin irritation, cancer, allergic dermatitis, and mutations. Various contaminants reside in textile effluent: glues, salts, acids, and auxiliaries. These substances are toxic, te- te- teratogenic, carcinogenic, and xenobiotic, responsible for creating eye burn, skin irritation, allergic conjunctivitis, burns, allergies, and immune loss, coughing, heart disease, and occupational asthma. In severe cases, consuming or inhaling contaminated water or chemicals and dyes from the textile industry can affect the central nervous system, liver, kidney, enzymatic system, reproductive system, chromosomes, and nervous system. Now, how can we solve the problems the textile industry causes? Well, most problems arise from textile effluent, so its impact on the environment and human health. And a solution is textile effluent treatment. Dye wastewater purification techniques are classified as follows: physical, chemical, biological, and hybrid. Physical approaches to to treat dye-induced wastewater include absorption, membrane filtration, and ion exchange. Absorption is the simplest physical treatment approach that uses adsorption such as alumina, zeolites, activated carbon, and silica gel. These adsorbents can effectively transfer pollutants from one phase to another. The ion exchange method provides an efficient way of removing heavy metals from water. Ion exchange can also remove azo dyes, but only at certain concentrations. Membrane filtration is another treatment method due to its tiny pore sizes and higher solutes that enhance color removal. Chemical approaches mainly comprise electrochemical methods and photolysis. Electrochemical technology is an enhanced oxidation technique that can eliminate organic pollutants from wastewater. Photolysis is a treatment method that uses high energy electromagnetic radiation, such as UV light, to generate hydroxyl free radicals as scavengers to remove pollutants. Biological treatments me- Biological treatment methods include microorganisms such as bacteria, yeast, algae, or fungi, or biological processes such as enzymatic degradation to remove pollutants from industrial wastewater. This strategy enhances decolorization and mineralization while minimizing pollutants that affect chemical oxygen demand, biochemical oxygen demand, and total suspended solids and turbidity. The mode of action involves the generation of hydroxyl and sulfate free radicals that facilitate the breaking down of pollutants into CO2 and water by electron transfer, radical addition, and hydrogen abstraction. Sorry. Hydrogen wastewater treatment systems combine traditional methods such as physical, chemical, and biological, addressing the deficiencies of individual methods and providing better effluent management solutions. The second mitigation technology method is waterless dyeing. Waterless dyeing techniques are key to decreasing the water used in textile dye processing. Waterless dyeing techniques like airflow dyeing machines are used to optimize dyeing fluids blended with high pressure airflow to spray dye over the fabric. This technology prevents water pollution, uses 95% less water than conventional methods, and eliminates bleaching and cleaning chemicals, all while bringing vibrant colors to clothing. Additionally, air dyeing reduces energy requirements by up to 86% and waste from extra outputs. So, in conclusion, the textile industry finds adopting more sustainable practices challenging with the ever increasing demand and quickly shifting trends. Nonetheless, the industry must prioritize assessing and moderating its overall impact on the environment in this rapidly shifting global climate. Investment in industrial pollution control technologies can help minimize the discharge from the effluents into water bodies. However, industries are reluctant to incorporate such technologies, citing higher production cost of goods. Therefore, there is a need to create policies that encourage industrial stakeholders to create proactive industrial processes and business designs. At a social level, educating and fostering the culture of adopting more circular strategies like reusing and recycling is necessary. Overall, the true sense of sustainability in the textile industry will involve combined effort from manufacturers, governments, and consumers. To end, I would like to thank my mentor for guiding me throughout this entire process, as her patience, knowledge, and willingness to help me whenever I was confused more motivated me to continue researching on this project and eventually finish it. Also, I would like to thank the Talaria Summer Institute for allowing me to research a subject I am captivated by, and for introducing me to my one wonderful mentor. This whole experience was something I am so grateful for and something that I will remember for a long time to come. Thank you so much.